In this video, I introduce normalizing flows for generative models. Considering the observations x, latent variables z, and model parameters theta, Q is the approximate posterior distribution of the true posterior P, where phi is variational parameters. To use backpropagation to train a generative model, we use reparameterization to introduce noise to a generative model. Normalizing flows find the variational distribution Q to approximate the true posterior P. The log marginal likelihood is defined as an objective function. First, we use chain rule to express this marginal likelihood as a margin of joint probability over Z. And using a factor of 1, we use Johnson's inequality to get a lower band of the log marginal likelihood. By using the definitions of KL divergence and Monte Carlo approximation, we use the sum of two terms to express the log marginal likelihood. The first term is a regular rider. The second term is a reconstruction loss. To use a gradient descent to train the model, we need to compute the derivative of expectation and select a variational distribution Q to approximate the true posterior P. Amortized variational inference combines Monte Carlo gradient estimation and the inference network to compute the derivative of expectation. Next, we introduce how to use normalizing flows to find the variational distribution Q. Normalizing flows uses the transformation of probability density through a sequence of invertible mappings to estimate the approximate posterior distribution Q. Suppose that a smooth mapping F and is inverse G if a mapping transforms the random variable Z with a distribution QZ. The resulting random variable Z prime has a distribution Q at Z prime. That expressed as a Q distribution at Z normalized by determinant Jacobian. For example, start from Z0 with a distribution Q. Normalizing flow uses transformation F1 to get Q distribution at Z1. That is used to approximate the true posterior. However, in practice, we need multiple layers to get a final Q distribution at key, that Z key, to better approximate the true posterior P. For example, using key transformations F key, start from Q0, we got Z key, and then now we substitute this Z key into the log variational distribution. We get this variational distribution Q. Using this relationship, we compute the expectation over Q0 without knowing Q key. Generally speaking, start from Z0, normalizing flows can guide the transformations step by step to anywhere we get Q distribution at Z key. However, in machine learning, we need to find the variational distribution Q contains the P, namely conditioned on the training data set. Similar to inference network, we define the F by using a nonlinear activation function H, where W, U, B are model parameters. a determinant Jacobian is computed by using this derivative of nonlinear activation function H. And now we got this determinant Jacobian, and substitute this determinant Jacobian into log variational distribution. We have this zk, and then now we have this log variational distribution qk. Once we get this variational distribution, we can use gradient descent to train the model. This flows modify the initial density Q0 by applying a sequence of contractions and expansions in the direction perpendicular to the hyperplane, which is referred to these mappings as planar flows. For more details, please check with these references. Thank you. Bye.